And then let's go ahead and get started with our new material. I do see that I have a few messages out there from people who did not get to the quiz with the holiday weekend. I know a couple people got messed up a bit on assignment due dates. So I know I have a handful of emails there. I will go through and do those extensions after this session. So I haven't been online since about noon. So if you emailed me this afternoon, I just got your message and I will get that done. Okay, so this week we switch gears a bit and we start talking for the next few weeks. We're going to talk about things that really kind of lead up to and explain how we come up with the numbers we do for the rest of the course. And this is the part that kind of changes the way we look at things a bit. And a lot of students struggle with this at first. We're going to talk about probability. Probability, there's a lot of different definitions, but one of them is the proportion of times the event occurs in the long run if the experiment is repeated over and over again. Well, what does that mean? Well, there's a lot of vocabulary in there. Really, what it means is just how likely it is that something will occur. But let's define some of that vocabulary we have. The experiment. Now, it's sometimes called a random experiment. This textbook calls it a probability experiment. And all a probability experiment is simply an action where we do not know which of two or more outcomes will occur. So with that, we should probably define what an outcome is. An outcome is just simply one possible result of a probability experiment. I know this sounds a little bit circular, but that's exactly what it is. The example might be the experiment is rolling a die. Simple six-sided die. Outcomes could be a 1, a 2, a 3, a 4, a 5, or a 6. Those are all the possible outcomes. Now, all those possible outcomes make up what we call sample space. It's just simply all the possible outcomes of a single probability experiment. So that's exactly what I just listed up above here for my outcomes for rolling a die. That is the sample space because it includes every possible outcome of that probability experiment. So there's a little bit more vocabulary to go here. An event. An event is either an outcome or a collection of outcomes from a sample space. So an example here, if we're still rolling a die, it might be rolling an even number. So the event there would be a 2, a 4, or a 6. That's the event. Remember, out of the sample space, and the easiest way to signify the sample space is also with those brackets, which is 1, 2, 3, 4, 5, 6. So you can see that event is just a subset of the sample space with one or more of the outcomes. We'll talk about combining those outcomes and to find the probability of an event later on. So a probability model. Sometimes called a probability distribution. Just like we had a population distribution earlier, we have probability distributions for a probability experiment. It is simply, it consists of the sample space and the probability of each outcome in the sample space. So it lists all of the outcomes and the probability of each of them. Now, there are some conditions on the probability of the outcomes. First, probability, and we're going to use some notation here. P and then parentheses, what's P stands for probability. What's in parentheses is what we're finding the probability of. Probability of a single outcome must be greater than or equal to 0 and less than or equal to 1. Now I'm just going to put P of O for for outcome. If P of O equals 0, that means it's impossible. Cannot happen. If P of O equals 1, that means it's definite. It's guaranteed. Either it's already happened or it's the only possible result of that action. The other, the sum of all probabilities of individual outcomes must add up to exactly 1. So if I'm rolling a die, P of 1 plus P of 2 plus P of 3 plus P of 4 plus P of 5 plus P of 6, that's the probability of each of the individual outcomes. They all must add up to be exactly 1 to be a valid probability distribution. Now, why is this so important? Well, because sampling from a population is a form of a probability experiment. Because we're randomly drawing from the population, the chances of getting a certain element with a certain characteristic deals with probability. So the qualities of our sample depend on these probabilities. Now, something that's really a big deal in statistics is something called an unusual event. All an unusual event is an event whose probability is extremely small. Well, how small? This depends on the situation. Usually, let's say, use an example of A equals our event. Then an unusual event would be the probability of A being less than or equal to 0.05, less than a 5%. Now, depending on the situation, sometimes we'll go less than or equal to 10% if it's not such a critical situation. Or if it's a really critical situation, we might go less than or equal to 1%. But typically, it's that 5% or 0.05 that it separates our unusual events from the standard events. We have different types of probability models. Now, each textbook calls these a little bit different. The first one is theoretical, or sometimes called classical probability. And this simply, first of all, this requires equally likely events. In other words, every one of the outcomes has the same probability of happening, just like rolling a die. Each of the 6 sides, if it's a fair die, have the same chance of coming up. So in this case, the probability of an event A is equal to the number of events, excuse the number symbol, containing A divided by the total number of events, total number of outcomes. So it's just quite a simple counting, basically, for theoretical or classical probability. So our example here, rolling a die. If we define A to equal the event of rolling an odd number, then P of A, well, there are 3 outcomes in A, and there are 6 total outcomes. So that's 3 out of 6 or 0.5 or 1/2, however you want to express it. Next, we have what this textbook, I believe, calls empirical probability, sometimes called experimental, or even relative frequency probability. And this is done from simulation or a high number of repetitions. So in this case, the probability of an event A occurring is equal to the number of times A occurred divided by total number of trials. So here my example would be rolling a die 600 times. The result of 4 occurred 120 times. So the probability of 4 would be 120 divided by 600, or 0.2. Now you might recognize that as being more than 1 out of 6. If this really were the case, we would start to question if that really was a fair die, if the probability of each value coming up was truly equal. And finally, we have subjective probability. Now, a lot of textbooks call subjective probability an educated guess. That's not totally true. It's a guess based on past results, history, and other considerations or other factors. So basically, most anything that involves like human activity, it really is a subjective probability. So examples, let's try to predict winner of a football game. What's the probability that team A wins? Well, let's look at history or past results. Team A has won 8 of the last 10 games between these two teams. But other factors, Team A's quarterback is out, is injured. So normally our history would say, well, Team A wins 8 out of 10. I'd say that's a 0.8 chance of winning. But with their quarterback hurt, that's going to reduce that. So we might take that down to from a 0.8 chance of winning to maybe a 0.6 or 0.5 chance of winning, depending on looking back through history again of how many games does Team A win when their starting quarterback doesn't play. There are some teams that never win a game if their starting quarterback is out. So that might really drop the probability of Team A winning from 0.8 down to maybe a 0.1 or a 0.2. That's subjective probability. We're taking all these factors and combining them, but how heavily we weight them is kind of subjective. We have to determine how big of a part they play in the overall probability. So what we've talked about so far is pretty much simple events. So what I want to talk about now is what happens when we get something called a compound event. A compound event is formed by combining 2 or more other events. My example would be flip a coin and roll a die. So this is a compound event. We have 2 results coming out. Look at all possible results. One way to get that is to use a tree diagram. So let's look at the coin first. So we might flip, so I'm gonna move over a little bit here. On the coin, we might get heads or tails. Well, then on the die, we might get a 1, a 2, a 3, a 4, a 5, or a 6. Is our possible results. Now we have to connect these. So we have heads and a 1, heads and a 6. I'm going odd intervals like this because my system won't allow me to overlap lines. I have a tails and a 1, a tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. And of course, these all kind of go back to the original start here. So let's list off my results. This is heads and 1. This is heads and 2, heads and 3, heads and 4, heads and 5, heads and 6, tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, and tails and 6. So this list here is all of my possible outcomes of that compound event. If I want to find the probability of rolling heads, well, I just look, there are 6 heads there out of the 12 outcomes, so 0.5. Oops, I got an extra decimal point in there, but you get the idea. Probability of rolling a 2, well, there's 2 outcomes in there that contain a 2 out of 12. So 0.1667, or 1 out of 6. Probability of getting a 3 and heads. Now here the keyword is and, means both must happen. Well, there is only one item in here that is both a 3 and a head. That's right here. So probability of getting 3 and a heads is 1 out of 12, or 0.0833. Let's look at the probability of getting a 3 or heads. So the key word here is or, means at least one must happen. Now in parentheses, I put or both because they can both happen. That still works. It's not what you would think of as a logical exclusive or, where it's one or the other, but not both. This is both, one or the other or both. So if we go over here and we look, well, these are all heads. This is actually both heads and a 3, so that definitely counts. So there's 6 heads, and then there's another one that's also a 3. That would be 7 out of 12, or 0.5833 is that probability. So the ands and the ors allow us to combine probabilities in these compound events. And the key is to remember, as we just said, an and, both must be true, both must happen. Or we just need at least one, or both can still happen, but at least one has to happen. And when we look at combining those, we look at some quirks here. The probability, if I was just flipping a coin, the probability of getting heads would be 0.5. If I was just rolling a die, the probability of getting the 3 would be 1 out of 6, or 0.1666, 1667. The probability of both heads and a die, or heads and a 3, we found by multiplying the 2 together, 0.5 times 0.1667. That gave us the 0.0883 or 833, sorry. The probability of heads and a 3, however, is not so easily combined. What we actually have there is 0.5 plus 0.1667. Then we subtract out the probability that they both occur at the same time, giving us the 0.5833. Now we're going to look at those two. This should be or, not and here. We're going to look at how those two are combined and why they're combined like that a little bit more here coming up. The first thing we want to talk about is something called mutually exclusive events. Mutually exclusive events are events that cannot happen at the same time. For example, rolling a single die. Probability that result be a 1 and a 2 is 0. You cannot have a 1 and a 2 on a single die. It's either one or the other. They both cannot happen. So mutually exclusive events, one of the definitions is events A and B are mutually exclusive if the probability of A and B occurring together is equal to 0. In other words, if one of the events happens, the other one cannot happen. So that's mutually exclusive. There's another thing called independent events. And this is not, these events are definitely not mutually exclusive. Mutually exclusive events are not independent. Independent events is where results of one experiment or one part of the experiment does not affect the probabilities of the other experiment or other part of the experiment, if you want to put it that way. An example here was the probability of getting flipping a coin and rolling a die. Probability of getting heads on the coin does not change the probability of getting 2 on the die. If you get heads on the coin, you still have the same probability of getting 2 on the die. If you get tails on the coin, have the same probability of getting 2 on the die. So no matter what you get on the coin, it will never change the probabilities on the die. I see we got some chat questions out there. Let's repeat quick. So when you add up all of the outcomes, they must add up to 1, the probability of all the outcomes. If the probability is 0, that means that they are not possible. Look at some of the other things there. Okay. So let's do another example that illustrates our independent and mutually exclusive. So the example we're going to look at here is marbles in a box. And we're going to have 3 red and 2 blue marbles in the box. Now, if I'm going to draw a single marble, the probability that marble will be red is just going to be 3 out of 5, assuming the marbles are absolutely indistinguishable except for color. So you can't reach in and feel the difference. If you're just going to reach in, shake and mix them all up, reach in and randomly draw one, there's 3 possible red ones out of 5 total marbles. That's a 0.6 probability. Probability that randomly selected one would be blue, there's 2 out of 5, or a 0.4. Now notice those are the only 2 possibilities. So we'll let X be the color and P of X be the probability. Probability of getting red is 0.6, probability of getting blue is 0.4. Notice each of those probabilities is between 0 and 1. And the total adds up to exactly 1. So that's a valid probability distribution right there. Okay, good. Well, let's take a look at some compound events. Let's draw out two marbles. Now, unfortunately, what we're saying, they're drawing out two marbles, is not enough to define the experiment. There are two terms we need to talk about. One is with replacement. What with replacement means is we put back the first marble and mix them up before drawing the second one. So if there's with replacement, that implies that there's something called without replacement. Without replacements means we do not put back the first marble. We leave it out and we go ahead and draw the second marble. So with replacement, what's the probability of drawing a red marble followed by another red marble? Well, for the first marble, there are 3 red marbles out of 5. For the second red marble, or second marble, now there's only 2 red marbles in there, and so this is still with replacement. So for the second marble, we drew out the first one. If it was red, we looked at it, we recorded it, and then we put it back in and mixed it up. So for the second marble, there's still 3 red marbles in there, and there's still a total of 5 marbles in the box. So this is 0.6 times 0.6 for a probability of 0.36. Here, the events of the first marble being red, the result of the second marble is independent of the result of the first marble. So see there's something in the chat. Let me take a peek. Oh, compliments come in. We're getting there in a little bit. So these were independent because the result of the first one did not affect the result of the second one. Without replacement, though, means that the first marble does not get put back. So the probability of a red marble followed by another red marble, well, for the first marble, there are 3 red ones out of 5. For the second marble, well, since we did not put the first one back, we assume that it's red. If it wasn't red, we don't even care about the second one because we can't get 2 red marbles anymore. But so we have to assume that the first one was successful. If the first one was red, that means there's only 2 red marbles left in the box. There's only a total of 4 in the box. So 3 out of 5 is 0.6 times 2 out of 4 is 0.5. That changes that probability of getting 2 red marbles to 0.3. So these are not independent events. So the other ones were independent because the result of the first marble did not change the probability of getting anything on the second marble. So technically what's going on here, if the events are independent, probability of A followed by B is just equal to the probability of A times the probability of B, which is exactly what we did up above. It was the probability of a red marble times the probability of another red marble. Gave us that probability of both of them being red. If they are not independent, we have to use something called conditional probability, where the probability depends on the result of a previous event. previous experiment. So the notation here, probability of the second marble being red, given that the first was red. So that's telling us that we have to assume the first marble was red to calculate the probability of the second marble being red. So here, technically, our probability of drawing two marbles and having both of them red was the probability of the first being red times the probability of the second being red, given that we knew the first was red. Up above, one other definition of an independent event is two events are independent if the probability of A given B is just the probability of A. Knowing that B has occurred does not change the probability of A. That's part of the definition of independent events. So this here is called the simple multiplication rule. And it is for independent events. This down here is the full multiplication rule. It is for any event, any pair of events. Well, we want to look, so this is when we have an and situation. We want both things to happen at the same time. Well, what if we go back to that or situation? We saw back here, go back one more, the probability of being a heads or a 3, we couldn't just add them together. We had this extra little factor here. Why was that? Well, if we have mutually exclusive events, when it's an or, the mutually exclusive plays into things. In other words, mutually exclusive means P of A and B equals 0. They cannot possibly happen at the same time. Well, P of A or B, probability of one or the other is just equal to the probability of one plus the probability of the other. This is called the simple addition rule for mutually exclusive events. Now, mutually exclusive events are not as common as independent events. The example here would be rolling a die. And the probability of getting a 1 or an even number. Well, they're mutually exclusive. No results are, 1 is not an even number, so we can't get both a 1 or an even number. So this should be the probability of 1 plus the probability of an even number. So probability of 1 is 1 out of 6 or 0.1667. Probability of even is 0.5. So that's 0.6667. If they're not mutually exclusive, so the probability of A or B starts out looking the same. It's the probability of A plus the probability of B, but we have to subtract out the probability that they both happen, because that would be counted twice. The probability of A and B happening is counted with the probability of A, and it's also counted in with the probability of B. So we subtract it back out. That's what we had to do before. We had the probability of rolling a 3 and the probability of flipping a heads. But then we had to subtract out the probability that they both happened because it was counted twice. It was counted in with the 3s and the heads. So we had to subtract that out. This is our full addition rule. So let's take a look a little bit more at some of our probability distributions. So let's look at a spinner, and I'm not going to show the spinner, but on this spinner, we can get certain values. Our values can be a 1, 2, 3, or 4. And the probability of getting each of those values, let's say it's 0.3, 0.4, 0.2, and 0.1. Now, all of those probabilities are between 0 and 1, and the total, if I add those all up, is 1.0. So it's exactly 1. So it's a valid probability distribution. So if I ask what's the probability of being a 2, well, I just get that right off the table, 0.4. What's the probability that x is less than or equal to 2? What's the probability of 1? Or the probability of 2? I can just add those up as well. Probability of being 1 is 0.3. Probability of being 2 is 0.4. Those add up to be a 0.7. If I had the probability of x being less than or equal to 3, well, then that could be the probability of 1 plus the probability of 2 plus the probability of 3. I could add those all up, 0.3 plus 0.4 plus 0.2 adds up to 0.9. Or we can use the complements. The complement of event A is everything that is not, I should say everything in the sample space that is not in event A. So for the probability of rolling of x being less than or equal to 3, the complement is x being equal to 4. That's the only result that's not in that event. We had the event, the sample space was 1, 2, 3, and 4. Less than or equal to 3 included the 1, 2, and 3. So 4 is the only thing in the complement. The probability of the complement plus probability of the event has to add up to 1. So P of A plus the probability of the complement of A has to be 1. So what that means more importantly for us is I can rearrange this. The probability of A equals 1 minus the probability of the complement of A. So up here, rather than having to add up probabilities of 1, 2, and 3, what we could have just done for the probability of x less than or equal to 3, we could have just said that this is the complement is x equal to 4. So probability that x is less than or equal to 3 is just equal to 1 minus probability that x equals 4. So that would be 1 minus probability of x equals 4 is 0.1, giving us 0.9. Now here, since our sample space only had 4 outcomes in it, only had 4 events, 4 outcomes, I should say. The complement was a little bit easier, but it wasn't a big deal. But if there were 20 events listed in that sample space, then it would be a big deal. If our the probability of being less than or equal to 18, well, we'd have to add up from 1 to 18. Or we could just say, hey, the only ones not in that event are 19 and 20. So the probabilities of 19 and 20 is the complement. We could find those two probabilities and subtract them from 1, and we would have the probability of being less than or equal to 18. So that probability of the complement is a huge, huge benefit to us. So the last thing we want to look at here is we want to look at contingency tables. Sometimes called two-way tables. They're called two-way tables because there's 2 variables being shown. So what we want to look at is students, randomly selected samples of students who took statistics and whether they passed or failed their first attempt at statistics. And what we're also going to look at is what school they are enrolled in within the university. Are they enrolled in the School of Business, School of Engineering, or the School of Liberal Arts? So over here, we're going to look at passed on their first try or failed on their first try. In the School of Business, let's see, in our sample, we had 62 that passed statistics on their first try, 19 that failed. School of Engineering, we had 54 that passed statistics on the first try, and 9 that failed. In the School of Liberal Arts, 79 that passed statistics on the first try, and 27 that failed. To work with this, we must have row and column totals. So let's do row totals. Well, let's see, is that 195 it looks like, and 55. Then we need column totals. So is that 81? Extend my window. 63 total engineering students. Liberal arts was 106 total students. And that adds up to a total of 250. So these two totals, adding up this way should be 250. Adding up this way should also be 250. So this number here is called the grand total, this one down here. And so that one should be the same adding in both directions. So let's find the probabilities. A student is selected at random. What is the probability the student passed? Well, we look over here. 195 students passed out of 250 total. So we have 185 out of 250. 0.78, I believe, is what that comes out to be. Or what is the probability that randomly selected student was from the School of Business? Oh, let's get rid of this marking here. We have a new one. So there's 81 from the School of Business out of 250 total. So that would be 81 out of 250. I believe that's 0.324 is that probability. So those are our simple probabilities. Let's do some compound events. Let's get rid of this. And let's ask, what's the probability their business school and passed? So now we're looking inside the table. We're only looking at those that are both business school and passed. Well, here's business and passed are these 62 still out of the 250 total. So that's 62 out of 250. So 0.248 is that probability. What if I asked, what's the probability of being business or passed? This is going to be a little bit trickier. So here's my business students. Here's the ones that passed. Notice I didn't include the totals there. So I have to add all of those up. So it's the 62 plus 54 plus 79 plus 19 out of the 250. Well, adding those up gives us, what is that? 114 out of 250 or 0. Come on, .456 is that probability. Now we could have found this an easier way. We could have looked at the row totals. Remember we said that the OR statement could be found by probability of being in business plus the probability past minus the probability of business and past. So what does that mean? Well, those that were business, there was 81 of those. That's this total right here. Plus those that passed, there's 195 of those. Subtracting out the ones that were both. Those are the ones that were both business and past, is those 62. Out of 250, the total. Well, adding those up, that still gives us 114. So that would be our same probability of 0.456. Now you might ask, well, why didn't I use the multiplication rule up here? Well, remember, the multiplication rule only works if they are independent. So for them to use the multiplication rule up here, since these may or may not be independent, we would have to do the probability. Here, let's do this. I'm going to move this down once we got room. Probability of business and past. We do the probability of the business times the probability of past given that they were a business student. So let's find that probability there first. The probability that they passed given that they were a business student. So let me get some of this marking out of here. What this means, the given that it's a business student, means we are only looking at business students. We're only looking at this row. Of those, 62 passed. So that means that 62, but it's only out of the 81 business students. So I'm gonna have to punch this in off screen. 62 divided by 81 gives me 0.7654. Is that probability? So that means this would be the probability of being a business student. We've already calculated to be 0.324 times 0.7654 equals, if I multiply that out, .248, which is exactly what we calculated up above. So we could use that multiplication rule there. It's just a little trickier because those are not independent. So we had to do that conditional probability right here. Well, since we did a conditional probability, let's look at the opposite of that. It's probably their business student given that they passed. Well, at first glance, a lot of people think, well, this is the same thing. It is not. What we're looking at here now, the condition is saying that they passed. So that means we're only looking at the students who passed. So we're only looking at this row. It's out of these 195 students. And of those 195, 62 of them were business students. So it's still the same 62 students, but it's out of the 195 that passed now, not just out of the 81 business. So 62 out of 195 is 0.3179. Now we can use that, however, to show that there is what we call commutativeness in our probabilities. Probability they passed and are a business student. Well, again, since these are independent, or not independent, I should say, it's the probability that they passed times the probability that they are a business student given that they passed. Well, up above, we did the probability that they passed is 0.78 times the 0.3179 that we just got. we multiply that out, we get, once again, the same 0.248. So these two probabilities came out to be the same. So it doesn't matter whether we do probability of being a business student in past or the probability of past and a business student. We change those orders, we still get the same combined probability. So there's all sorts of different combinations we could go through here, but we're not really going to get into that. I mean, they're all really just variations of the same calculation. So the last thing we want to talk about is something that the textbook does not really cover well. And this is something called Venn diagrams. A Venn diagram is a way of mapping out the population. And it shows using an area model to illustrate the population. And I say visual model, area model. Some of them are the area is meaningful. Others, we try to make it meaningful, but it's not necessary. It's hard to get them out drawn to scale. So let's look at cars on a used car lot. Let's say that we have 90 cars. 36 have a sunroof. 28 have a trailer hitch. 9 have both sunroof and a trailer hitch. So the question is, how many have neither a sunroof or trailer hitch? Well, this is where the graphic comes in. So let's say that this is our 90 cars. Put this outside that. Inside the circle, or inside the square here, we have 36. That takes up about a third. They have a sunroof. Now, then we have 28 that have a trailer hitch. Now, if there were none that had both, we'd just put the circle over here. That'd be our 28 with the trailer hitch. That'd be the end of it. But there are some that have both. So we overlap. So let's do this quick. These are my 28 with the trailer hitch. There's 28 of them. But again, there's some that have both. So these circles actually overlap. And there's 9 that have both. So what that means is that 9 does not just materialize out of thin air. We've got to reduce this number by 9. There's only 27 that have a sunroof without a trailer hitch, and another 9 that have a sunroof with a trailer hitch, giving us the total of 36. Out of our trailer hitch here, we subtract from the 28 to get 19. There's 19 that have a trailer hitch and no sunroof, another 9 that have both. So that's 9 and 19 make the 28 total with the trailer hitch. So if we add those up, that's 27 plus 9 plus 19. That adds up to 4655. So that means the rest, 190 minus 55, or 35, have neither the sunroof or the trailer hitch. So that's how many are left outside the circles here. There are 35 with neither. So that's a Venn diagram. So use that visual. And the key is you have the two possibilities here, the sunroof and the trailer hitch. They each have their own circle. And you start out with the circles being separate. But then the fact that there's some that have both, we have to overlap them. And to populate this overlap, to find out how to put the number in this overlap, we have to subtract it from both of these because it's counted it in both of them. A way we can think of this is what we did with our addition rule. The ones that have sunroof plus the ones that have a hitch minus the ones that have both. So we had 36 with a sunroof plus 28 with a hitch minus 9 that had both. That would give us that total of 55. That's exactly what we found down here. So it's kind of the term used for that in some books. This textbook doesn't really use it, but it's called inclusion exclusion principle. And that's just the Venn diagram is just a way of illustrating that, of showing that when you have items that fit both characteristics, they reduce the amount in each group to make that overlap. But still, it's still 27 plus 9 or 36 with a sunroof, and 19 plus 9 or 28 that have the trailer hitch. Okay, that is all of it for this week. Like I said, be patient with yourself. Probability is a different way of thinking. And this is really generally where students start to struggle a little bit more. So I highly encourage you to start on the homework early in the week so that you have time to ask questions, because this is, again, where people start to get bogged down. Does anybody have any questions here before we stop the recording?
I have one question.
Sure.
Okay. So the simple multiplication rule
Yep.
applies to independent events, but the full multiplication rule applies to what aspect again?
So the simple multiplication rule is only for independent events.
Mhm.
The full multiplication rule applies to any pair of events.
Thank you.
Any other questions?
I just have a question about the it's not about class, so I can wait until
Oh,
it's
go
over.
ahead.
Pertaining to extra credit, if I asked the question and then found the answer like 20 minutes later and answered my question, does that count as extra credit?
That definitely counts, because that happens to me all the time. Sometimes the question is no more than out of my mouth and it clicks in as to what the answer is.
Yes.
Or like you said, you ask the question and, well, you're not just going to sit around and wait for someone else to answer it. You're going to keep looking for it until you found it. So I actually do really appreciate when you do post your own answers. That helps out everybody else a lot more. So yes, definitely get the extra credit for that.
Okay, awesome. It just hasn't been put in yet.
I have not got this week's done. No, with the Labor Day weekend, I was a little slow this morning getting stuff done.
Oh yeah, no worries.
Sure.
I'm sure you've been really busy.
That's the one problem this year. It really hit because 4th of July was on a Monday night too. That's the one problem when classes select Monday for their lecture time is you get Memorial Day, Labor Day, and this year it was also 4th of July. It's tough. 4th of July is really a bad one to get people to show up for an evening class. So it really does kind of mess things up a bit.
Yes. I'm trying to think if I had any other questions about this past week. I don't think I do though, but okay.
Well, if you think of any others, you can feel free to send me an email and I can answer them that way too for you.
Okay, thanks so much.
You bet.
This might be a dumb question, but the general addition rule,
Yep.
it's inclusion and exclusion. That is completely different from what was the word? Mutually exclusive, right?
Yes.
Okay. Can you remind me
So the
General-
general addition rule, again, applies for any pair of events. That's where the inclusion exclusion was the probability of A or B is just probability of A plus probability of B. That's because, oops, sorry, probability of A plus probability of B minus the probability of A and B. The simple addition rule applies only if A and B are mutually exclusive.
Okay.
In other words, probability of A and B, the probability of them happening together is 0. They cannot happen at the same time. So that's just probability of A, or the probability of B is probability of A plus probability of B. Notice it's really the same thing. It's just this factor would be 0 anyway, so we don't put it on the end down here for this formula.
Okay. Thank you.
You bet. Typically, what I tell students, if they're confusing you, just remember the general rule for both of them. Use the full rule or the general rule, and it'll work out. It'll still work out. You don't have to memorize when to use which one. Then just go ahead and use the general rule in every case. And like I said here, this just turns out to be 0, so you still get the right answer.
Perfect. Okay. That makes more sense.
Sure. Any other questions?
No, but thanks. I hope you have a nice night.
You're welcome. You too.
All right.